All right, welcome everyone to the first CRM seminar in applied math in 2021. And it's my great pleasure to introduce our first speaker for this season. And that's Courtney Paquette, who is a colleague of mine at McGill. And just a couple of words on Courtney. So Courtney got her PhD in 2017 at University of Washington with Dima Druzviatsky. And she had postdoc stints with Katja Scheinberg at Lehigh and Steve Vassis at U Waterloo under an NSF postdoc grant. And then she moved to Google Brain in Montreal in 2019. That's also when we hired her. And then she joined Math and Stats at McGill in 2020. And we're very happy and lucky to have her. And Courtney's field of expertise and research interests are broadly in continuous optimization with strong applications in machine learning. And yeah, so the stage is yours, and let's all enjoy Courtney's talk.
Great. Thank you guys for having me here. I'm very excited to give a talk. Even I feel like I don't actually know anyone at McGill very well. Well, okay, I know Tim and Jessica, but after that, it's a little bit less since I haven't actually been to my office, nor do I actually have an office at McGill yet. But today I wanted to talk to you guys about some cool, interesting research that I've been working on halting time for large models. This is related to average case analysis. If you guys attended John Ducey's talk last term, this is sort of a supplement in some ways to what he was talking about. And so this is joint work with actually a graduate student who's joining McGill, Q1, and then some colleagues of mine at Google Brain, which is Bart and Fabian, and then Elliot, who's in the background, also contributed quite a bit to this stuff. So the idea with optimization is that we're trying to minimize some function f of x. And we want to understand sort of the complexity of an optimization algorithm. So the goal of this talk is to understand the idea of average case complexity. So what do we mean by that? So this is the idea that the complexity or runtime of an algorithm is sort of averaged over all of its possible inputs. Okay? And why is this important? This is important because it generally is more representative of the typical runtime of a user, right? You're going to usually see the average case. Okay. Now, what's interesting is that if you look at the history of continuous optimization, we almost never talk about complexity results in terms of average case. What we generally talk about complexity results are in the worst case, in the sense that if we take sort of we look at the algorithm, we compute sort of the worst case function, and we compute sort of the runtime of it. Oh my gosh, sorry, my computer, is anyone seeing this? I have some random update appearing on my screen. Sorry. So again, most of these results in continuous optimization are for the worst case. So they're generally not typical behavior of the runtime. There's been a lot of work on average case analysis. So probably the most famous sort of version that like at least students have heard of is sorting algorithm. So Quicksort is an example of an average case analysis. But in optimization, sort of the closest version of average case that we have is on the simplex method. This was done via smooth analysis. I'm not going to deal with smooth analysis, but you can see an average case for a simplex method, which does a lot better. And then recently there's been this really push, John was talking about this as well. There's this push to sort of understand more typical runtimes of these algorithms. And so people have been looking at this for a little bit of time. And for instance, Trogdon and Deft have been doing this with CG. Elliot did a little bit with CG as well for these runtimes of these algorithms. Okay, so how do we do the typical behavior of an optimization? algorithm. Why aren't we using this more often? Well, there's really three big difficulties with this. The first is that, what do you mean by a typical problem? What does it mean by a typical function? Like, is it convex? What is a typical strongly convex function? It's not entirely clear. The other thing about average case, which has always bothered a lot of people, is that there's this sort of feeling that it should depend on the probability distributions that you're putting into the inputs of your algorithm. Okay, so like somehow it's the distribution dependent, a complexity result. And then of course you might still say, well, how much does this average complexity coincide with what you observe in practice? Okay, so how much does it actually appear? Is this really representative of typical runtime? And so like we were like, okay, what should we do? How should we start addressing these problems? So the first thing we were like, let's address what do we mean by a typical convex problem or strongly convex problem. So what we did is we thought, what is the easiest convex problem that we could work with? So what did we decide? We decided least squares. Okay, pretty easy problem, right? You have just you're minimizing ax minus b norm squared. Okay, and when you're doing the least squares problem now, you can easily see what you mean by an input, right? What do you mean by random inputs, right? The input here would be the matrix A and the vector B. Okay, so here we're going to assume that we have a random matrix A and a random vector B. Okay, and when we measure complexity of these algorithms, we're looking for when does it get near optimality. So we're wanting to understand what happens when the gradient is small. Okay, so I'm going to look at the halting time. And we ran this and we saw some super surprising results. So this is a picture here. We're running gradient descent. So this is just moving in the direction of negative the gradient. And what we did is we generated lots and lots of random matrices A, okay? And we generated them in various sizes, okay? So for each size matrix, we generated 16,000 matrices A and B, and we ran gradient descent on it, and we computed the first time that this gradient was less than epsilon. Okay, and we recorded it here. So from 2 to the 5th, that's at the bottom, that's the model, that's the dimension, it's a number of parameters. This is the distribution of the halting time. And what we saw was something, what's the distribution? I'll explain that in a second, but what we saw was something super surprising. What we saw was that the halting time is somehow predictable, that as you make the dimension larger and larger, which is what happens now in machine learning, dimension here being n, it's really about the number of samples, number of data points, you're working in large dimensions, it becomes very predictable. The halting time is always the same, no matter what. The other thing that we saw, which is also very interesting, is a universality, which is that this value that the halting time was converging to doesn't really depend on how you chose A. So this is a question to someone who's asking here. The random A is kind of, it doesn't actually depend so much on it. Okay? And I'll explain exactly what I mean by that. There is some information there. So how do we do our model? Okay, so here again, we're minimizing this least squares. How do we generate this random matrix A? How large is D? I'll explain too. We use the generative model. So the generative model that we use here is that we're going to take a signal, a random x tilde, and we're going to generate B by looking at AX tilde plus some additive noise. Okay, so B is generated sort of by a signal plus some extra noise. And we're going to also have a random initialization of our algorithm. Okay. And what the assumptions that we made on our signal and our noise, well, we normalize the signal. We normalize the signal to noise ratio. So what this means is that as you increase the dimension, okay, what's going to happen is that the amount of signal and amount of noise kind of stays constant as you increase dimension, as you get bigger and bigger. This is just sort of an assumption we made as a modeling assumption. In terms of how we did D, it's a very good question. Because we're dealing with random matrix theory, we're actually going to make the ratio of D over N be constant. So the ratio of D over N is going to converge to some constant, R. Okay. So what type of data distributions are we considering here? So what does one mean by sort of a random A in some ways? So the typical thing in random matrix theory is to assume that the entries of A are IID, mean zero, fixed standard deviation, and have some sort of finite fourth moment condition. Okay, so this is sort of the classic one in random matrix theory to model things based off of. If you want to get more interesting things which are more related to sort of the machine learning community, we can also model A by looking at the entries of Aij and taking sort of an activation function. So what you do is you take two random matrices, you multiply them to each other, and then you do a pointwise or entry-wise activation function on it. When you write down the least squares problem, what this corresponds to in sort of a machine learning terminology is that you're sort of randomizing the first layer of your weights, and you're just minimizing over the last layer. So this is sort of a model for the machine learning type community. Okay. And someone was asking this second, what do we actually need about our random matrix A? So what we're going to assume is that we need that what we're going to look at from the random matrix theory point of view is that A transpose A. And why does this A transpose A appear? Well, it appears because if you take the gradient of the least squares problem, you're going to see something like A transpose A appear. Okay? And the general modeling assumptions we're putting on this data are that the ratio of the model size, D, versus the number of samples converges to some R, okay? So some fixed quantity. That's how we're going to make things grow. The second thing we're going to assume, which is true for these two models that I told you guys before, is that the empirical eigenvalue distribution actually converges to a compactly supported measure. Okay, so here you're putting delta masses at each of the eigenvalues of H, and you want sort of like the normalized or maybe the trace of it to converge, another way of thinking about it. The other assumption that I'm going to make here is something about the largest and smallest eigenvalue. I'm going to assume that sort of the largest eigenvalue converges to sort of the upper edge of my compact supported measure. Okay? And the same thing about the smallest one. Okay, so like you're like, okay, that's great. I think some people are asking some questions. Maybe I'll ask, there's a finite fourth moment condition. There's a finite fourth moment condition because I want this convergence. So this is a random matrix theory. Sorry, you're probably asking why the finite fourth moment condition on the isotropic features, I assume. It's because it's a random matrix theory. If you have too much of a tail in your distribution, you won't get convergence of the empirical measure. It just doesn't converge, or it converges to something else. Okay, so why are these things important? Yeah, that's the question. Or how do we actually, where do we see these? If we look at the isotropic features model, what those things that I just said, there's actually an explicit measure associated with it. So again, I'm going to let the model size D over N converge to some fixed R. Then it is well known that under isotropic features, under these like finite fourth moment, that the eigenvalues of A transpose A converge to a fixed known probability distribution known as Marchenko-Pasteur. It is completely well known. And this is a picture of it. Okay, so this is a picture as you vary R, so as you vary the difference between the ratio of D over N, you get this sort of distribution for the eigenvalues. Now, this is actually a pretty important distribution. If you talk to physicists, I feel like they always say that everything is Marchenko-Pasteur. Not sure if that's entirely true. I'm sure people will disagree, but it's been shown, in at least empirically, in sort of these large neural network things, that if you look at the Hessian of your objective function and map the eigenvalues, so graph the eigenvalues of it, then the distribution does look like a Marchenko-Pasteur with some outliers. Okay. Okay, so this idea of the Marchenko-Pasteur measure is actually pretty important. You actually also see it in optimization. So this is on real data, everything. It does look like a Marchenko-Pasteur. If you are assuming sort of like sparsity or something else, like sparsity in B, you're going to get a different measure than the Marchenko-Pasteur. Okay? So it just leads to a different distribution. Okay, so again, the question that we're interested in is sort of how do we actually show this really cool concentration type result? I think it's really cool. You can see it's converging. So what do you actually do? So we're going to go old school numerical analysis here. And we're going to go back to this idea of when you're trying to solve something like AX equals B, that any sort of method which just depends on gradient information can be written as a polynomial in the matrix H. So every first order method for these squares has an associated polynomial in the matrix H. Okay. So just example, gradient descent. What is gradient descent? You're just going to move in the direction of negative the gradient. So that's the first line. I'm moving in the direction of negative the gradient. Okay, I just plug in what the gradient is. When I plug in what the gradient is, I get identity minus h times what I started with. I iterate that down all the way back down to x0. And what you see is, again, you get this polynomial, which is identity minus h to the k plus some noise term. The noise term is because the b also has noise. Now, what turns in important here is that this noise term is also a polynomial in H. Okay, so what this tells you is, again, that every first order method, we have a polynomial H, and this is very explicit, and this is well known. So this is basically how you prove like conjugate gradient methods a long time ago. But you can do this with every first order method. So I realize that not everyone is familiar with these first order methods, but if you are familiar with it, we don't analyze in today's sort of techniques, we don't analyze these methods using polynomials. But you can write them all down. So I think probably the most interesting ones are sort of like Nesterov's momentum type methods. So if you look at Nesterov's and the convexity, this is an algorithm that works when your matrix A is not positive definite. You can write down the polynomial. It's an extremely complicated algorithm. And the polynomial happens to be differences of Legendre polynomial. Kind of weirdly, it's a difference of Legendre. You can do these with Polyak and Nesterov and the strongly convex. So these are algorithms which work for positive definite matrices. And the polynomials, as sort of you might expect, are Chebyshev polynomials. Okay. Now, what is really interesting about all of these methods, and what is kind of important here, is that all of these methods sort of decay, their polynomials decay exponentially, in the sense that if you look at what happens at the largest eigenvalue, when you get k far enough, you've sort of killed out that largest eigenvalue. So what that means is that most of the mass of these polynomials occurs near the smallest eigenvalue. Okay. And you can graph these. They're kind of fun to graph. You can see all the things. And as you guys might expect, and probably from people, kind of what I said, there's kind of like this thing where they decay exponentially, so that at the largest eigenvalue, they're basically going to zero, and so all their mass is somehow concentrated around the smallest eigenvalue, or around zero, in that sense. And so what ends up being really important in all these algorithm analysis is actually that the asymptotic behavior of these polynomials near zero. And so when you look at them, they're all Bessel functions of different types. So analyzing these things are just analyzing Bessel polynomial functions. Kind of interesting on a side note. So how do you do this? Well, it turns out that to analyze the typical behavior of an algorithm, we can look at various things. And in this case, I'm going to focus on the gradient, the norm of the gradient squared. And when you put in all of these sort of assumptions and randomness, you can actually show that the gradient is just basically equal to the trace of this polynomial in H. Okay? And so because of that, the gradient then just depends on the spectrum of this matrix H, the spectrum of your data in some sense. That's all that it depends on. And what we assumed about our H was from random matrix theory, you know, if you have this random H, you can have this empirical distribution of your eigenvalues, you know that it's going to converge to some fixed distribution. So this trace is this polynomial H because it just depends on the eigenvalues of a random matrix. It's going to converge to something concrete. Okay. And that's actually what we showed. So this actually gives you the concentration result. So what we showed is that the gradient converges as you send the number of samples to infinity to a fixed determined quantity. And that quantity, you can explicitly see how all parts of like your inputs of your algorithm affect that convergence rate. So you see how the signal affects it. You see how much if you added that noise affects it. Your algorithm affects it through the polynomial itself. And then the spectrum, which is kind of cool, you see how the spectrum directly affects the algorithm's convergence through this data model. Okay. So it's a really cool, because you get, this is explicit, this is equalities in some sense. There's no bounding whatsoever done. The gradient is exactly equal to this in the large scale model. And once you do this, it's really easy to get the halting time result from it, because sort of this right-hand side is your expected time. It's your expected it's what the expected gradient should be. So the halting time then is just the first time that quantity is less than epsilon. And just because of that convergence that we have, you get that with probability 1 that this gradient, the first time that the gradient is less than epsilon is going to be some deterministic quantity. Okay, that's pretty cool. I don't know. First time I was like, this is really amazing. In optimization, I don't know how much I can emphasize this, but we've always known for a long time that every optimization algorithm depends on the spectrum of the data, but usually we think of it as just on the largest and the smallest eigenvalue. But what this actually shows you is it shows you exactly how the full spectrum, how every eigenvalue in some ways contributes to the convergence of the methods, which I think is really cool and was missing for a long time in optimization theory. And then just to show you guys again, here are some examples of this. So you see the halting time above. What I plotted below here is sort of the distribution of the halting time. So for each fixed n, I kind of plotted. So what happens over time as you make n get larger, it actually becomes more normally distributed. It's kind of cool. It also doesn't take very long for this to happen. You know, basically by n is equal to 1,000, you're at a deterministic quantity because it's random matrix theory. Here's what happens in Nesterov. We had some weird numerical issues with student T, because if you're in like a smaller dimensional matrix and you generate student T entries, there are entries of it which are really, really large, and they actually do appear. They're not like low probability events, but they actually really do appear, and they affect your convergence rate dramatically. But as soon as you kind of like get large enough, they all disappear. So this large scale limit is really, really important. You might say, wait a second, this only applies to least squares. It seems like this might be a little bit funny. In fact, we saw this sort of type of behavior in almost all sorts of functions. So logistic regression, which is classic one, and then SGD too, which is a stochastic algorithm. So it's pretty amazing. And maybe I should pause here. Is there any questions, or is everyone, am I going too fast? Does it make sense?
Oh, I have a question. So is convexity always there for
Yes.
the objective?
Yes, so you can assume that the objective function is always convex. It doesn't need to be strongly convex. The reason why you can assume sort of convex is because in the limit, as you take a random matrix, the distribution of the eigenvalues can become arbitrarily close to 1 or arbitrarily close to 0. So the smallest eigenvalue can get really, really small. And as a result of that, it exhibits the convex behavior that you see. That's a good question. Are there others out there? No? Can we move on? Okay, cool. All right, so this gives you average case complexity. So here I'm just gonna do it for the isotropic features model, just because we have an explicit formula for that measure. And so recall that in the isotropic features, so this is the IID entries of the matrix A are IID, mean zero type things. then the empirical distribution of these eigenvalues of H converge to this well-known marching capacitor. And this is kind of what I was just talking about. When you said, so if we look at R as the model size over the number of samples, when you send R equal to R to 1, what happens is that the gap between 0 and the next smallest eigenvalue disappears. So when R is not equal to 1, there's always sort of a gap which exists between 0 and the next smallest eigenvalue. So in that sense, when R is not equal to 1, you're kind of in this strongly convex. You have sort of H is really, you know, it's positive definite. It's positive. But as you send R going to 1, it stops becoming positive definite. It starts to have eigenvalues which are extremely close to 0 and essentially behave like they're 0. Okay? So as a result of this, we expect to see different convergence behaviors when R is equal to 1 and R not equal to 1. Okay? Because in R not equal to 1 case, we're getting something more like a strongly convex, a positive definite matrix. And then in R is equal to 1, you're getting something more like a positive semi-definite matrix appearing. And you see this is extremely apparent in the complexity results. So what we did here is we varied the R. Okay, so R is on the x-axis, and Y is the halting time. And you can see that when R is equal to 1, you get this giant spike. Okay? And then it kind of goes down afterwards. And you can also see how the effect of noise. So the green one has the most amount of noise. The blue is not as much. But you see this, always see this spike. Now this spike is this sort of up and then back down curve. If you're in machine learning, you will have seen this before. This measurement R is sometimes related to generalization properties because you can think of it as sort of measuring the capacity of your network. But it also affects convergence rates. So it's kind of an interesting quantity and certainly something to look into going forward. So how do we compute the average case? Oh, someone have a question? Sorry.
Quick question, Courtney.
Yeah.
Can you go back to the slide before?
Yeah.
But this spike is at R equals 1, you said, which is like the non-strongly convex case.
Yes.
It does not have anything to do, because usually you expect that the convergence could be really bad if it's just badly conditioned, but that doesn't come into play here somehow.
Well, it does. So when it's badly, again, it's all about the ratio of R. So when it's badly conditioned, it means that you're very close to R is equal to 1. Right? So a badly conditioned matrix is something which is close to R equals 1. Better conditioning means further R away from 1 in either direction.
Okay, you're saying you can only get R exactly 1 if you're non-singular, if you're singular basically, but you could get arbitrary closed with bad conditioning. Yes.
So the way that it works, and this is actually why this model is kind of a nice thing to use, because it like kind of models all the stuff that we're used to, is that as R gets close to 1, the gap between 0 and the next smallest eigenvalue goes to 0. This gap shrinks.
Okay.
So as R gets close to 1. And so in that sense, you can measure bad conditions and monitor sort of how the complexity changes based upon badly conditioned. It's actually, this model is really cool. These are like I know this sounds super weird, but this is actually like exact equality. Like you can actually see, you should be able to see everything. You should see how the spectrum affects it, how the algorithm, how badly conditioned the matrix is. It will be in this formula in some ways, which is cool. Yeah, sorry, are there other questions?
I have a quick question. So
yeah.
Larger the R, the ratio, more difficult the problem, right? The dimension.
No, so this is sort of the counterintuitive, but so this is counterintuitive too. I think for machine learning people, they've seen this so many times. They're like, yeah, I know what this is. But for other people, it feels counterintuitive. Certainly the first time I saw it. The larger, it's not about larger the R. It's sort of the further away R is from 1. So when the further you're away from 1, the bigger this
in
gap
either
actually.
side, right? Either
Yeah,
side?
on either side, exactly.
Oh, okay.
So if you make R really, really large, it's good. If you make R really, really small, it's also good, as long as it's away from 1. And the reasoning is from random matrix theory is that this gap. So this gap is like only, it's on both sides. So as R comes to 1 on either side, that's when the gap shrinks. Otherwise, there's always a gap between the two.
And how fast the gap goes to 0 as R goes to 1? Just you know, generally.
Yeah, so this is sort of the smallest eigenvalue conditions. I forget, there's like an n dependence. Probably someone here who knows random matrix theory, like Elliot, would be able to tell me exactly the rate of convergence.
Okay.
But it's known. It's well known. How about that?
Okay.
Yeah, it's a good question. Yeah, and maybe just to point out, so I guess it feels counterintuitive because you think like, well, if the number of samples gets large, it's kind of bad, or if the model size gets large, it's bad because you're over parameterizing. But it's this weird thing of observation in machine learning that we've seen, which is that over parameterized models don't actually hurt you very much. And so this is kind of a measurement of that quantity. So then, oh yeah.
It's not related to the condition number of the matrix. It's related to the gap between 0 and the next non-zero value.
Yeah. So the R is sort of related to the condition number. Yeah, that's exactly right. Yeah. But the other people,
because you are saying that it depends on the gap between 0 and non-zero eigenvalue. So it's not between 0 and the largest eigenvalue.
That's true. Yes. This is sort of so in optimization, it's always been like it's about the smallest and the largest eigenvalue which matter, like the difference between this. This is kind of saying that that's not entirely true, or at least what actually affects it is there's more affecting it. There's more of the spectrum affects it in some ways than just knowing the gap, knowing the largest and smallest eigenvalue.
And do you get any Tracy Widom coming in at any point, or
that we're hoping. Well, there's more extension, so yes, it's a good question. Yeah, it's a very good question. It's something that we want to use more. People don't use random matrix theory very often in optimization, so this is kind of our first sort of easy attempt at it. But yes, yeah. So again, sorry, thank you guys for all the questions. I appreciate it. Yeah, but the smallest Tom is here. Thank you, Tom. The smallest eigenvalue is 1 minus square root of R. Yeah, that's right. So to compute the actual average case complexity, we just need to understand sort of what happens on the right-hand side. Okay. And so all we have to do is we have to just plug in d mu, our Marchenko-Pasteur, and you can do that. And so I wanted to talk a little bit about how traditional worst case complexities are. So in traditional worst case complexity rates, they're generally given by the distance to the optimum. And what can happen in these random matrix models is that the distance to the optimum is actually a dimension dependent constant. So it's a little bit hard to compare worst case and what we did in the average case where we took n to infinity. Okay. And you really can see this dimension dependent constant. So this is sort of showing when you have this, if you just sort of took the worst case complexity rate and graphed it, it's extremely sporadic, it's crazy, it's all over the place, it's not concentrated whatsoever, and it's going to grow. Whereas if you actually did sort of what we have for our average case rates, you won't see that. There won't be this, they're exact in some ways. So there's some dimension dependent. We then tried to, because we were trying not to be so unfair to traditional worst case rates, which has a dimension dependent constant in it. We decided, well, maybe the better way to compare an average case is to kind of sort of take the polynomial that you get and compute sort of the worst eigenvalue. So the maximum of that polynomial can be over a fixed spectrum support. So if we fix the support to be the same as what we got, we'll just take the maximum of our polynomial, and that would become sort of the worst case, and in that way we get rid of this sort of dimension dependent. And when you do this, you can compare things. So in gradient descent, you can see in the worst case you have this dimension dependent constant, and in the average case you actually get some improvement. So you get this k to the 3/2, which is kind of cool. Same thing with Nesterov's. You get sort of a dimension dependent. It's like a 1/k cube. You actually get you get better in the accelerated case. So it's kind of a cool thing to do. And what does this all matter? So when you do strongly convex objectives, so these are positive definite matrices, you don't really see that much improvement between the worst and the average case. Where you do see improvement is that you get sort of the same rate, a linear rate, times by a polynomial rate. And you actually get to see that polynomial rate. So for instance, in gradient descent, you see that it still has this dependency on the smallest and largest eigenvalue, right, on the rate. And then on the average, you gain a little bit in that polynomial term, okay? So the gain of understanding, seeing the whole spectrum is actually in polynomial terms. But because convex, you're always only working with polynomial complexity rates, this extra term actually affects your average case rates.
So what's the definition of R squared?
R squared, sorry,
signal.
yes. Yeah, it's a signal. It's the size of the signal. So R squared is the size of the signal, and R tilde is the size of the noise that you added to the B. So it's kind of like you have a signal plus noise term.
So what do you mean by the size of the signal?
Yes, yeah. We did it so that you could do it, you could see the rate, what would happen when R tilde was 0. It doesn't matter in these cases, but when R tilde is actually 0, you have no noise in your B whatsoever. You actually gain more in the polynomial term. So these terms all grow by a little bit. You can see you get a 1/k to the 4th versus a log k over k cubed, and that's just because you have no noise in the B. It's kind of cool, kind of fun. Tom is an expert in this. Cool. Any questions? Maybe I should pause for a moment since I'm getting lots of things. Everyone okay? Cool. Okay, so I wanted to just end with something which is a complete work in progress, but I thought it was really cool and interesting, and I know there's probably people here who might be interested in this. We wanted to do the most classic algorithm, which is stochastic gradient descent for machine learning problems. And the idea with SGD here is we can see that we're looking at a sum of sort of AIX minus BI squared. That's the same as minimizing the norm of AX minus B. I know I wrote it in a funny way, but it's to make it fit into an SGD format. So we can think of this as a sum of F sub i's, where I've made F sub I be AIX minus BI squared, norm squared, or squared, okay? So what SGD does, the general algorithm, is it's a stochastic algorithm. So what it does is it chooses an index I uniformly, okay, in N, and it just picks that I and moves in the gradient, it computes the gradient F sub I of X and moves in that direction. So it doesn't compute the full gradient of the function. It just computes a single sort of entry, gradient entry, okay? So it goes xk plus 1, you just pick an I and move in that direction, okay? And you can rewrite that in terms of on this left-hand side, where gamma here is going to be my step size. So how much in the direction of my gradient I'm actually going to move. Okay, so you can do this whole analysis for SGD. it's way more complicated, because now what you have is you have randomness already pre-built into the algorithm on top of the fact that the matrix A and B are random themselves, okay? So there's a whole bunch of randomness. But what's crazy about this is you can actually compute what the sort of limiting behavior of the function values of SGD. And what it turns out to be, is that it turns out that the limiting value of SGD is a deterministic quantity, but the quantity that it converges to is the solution to a Voltaire equation, not an ODE, which is generally what it's considered. It's actually a Voltaire equation, okay? Like a pure old school Voltaire. It's not even just like Voltaire, like the general Voltaire, it's even a nicer Voltaire. It's a convolution type Voltaire. It's a renewal equation. And so it's super cool. So you can actually see the long-term behavior of SGD, the dynamics of it are. And this is with step size not going to 0. So this is really cool. It's a really neat idea. And by the way, if the only thing that's stopping us for the Voltaire equation right now for sort of long-term limits, which I'm hoping maybe some applied math people here might know, is that we have some trouble actually solving numerically this Voltaire equation. So if you have a good numerical solver for Voltaire, I'd be interested. So I wanted to give you sort of just some graphs of kind of what our model, what this Voltaire does compared to sort of the typical models for SGD. So we are the blue, and if you run SGD, it's like the orange curve, and you can see that they're like always on top of each other for various step sizes. There's an SDE model for gradient or for stochastic gradient descent, but it requires the step size to go to 0. And so it has some problems when you have large step size, which is what you generally have in practice. It doesn't seem to converge to the same quantity. It's super weird. We seem to be really accurate with this Voltaire equation. I think this is really exciting. It's amazing. No one's seen Voltaire. Everyone thinks of it as a SDE. So it's kind of cool that it's not an SDE that SGD is converging to. And you can do this for large step sizes. Which is most amazing. And then what actually turns out to be even more weird about SGD, and is a feature maybe from mathematical physics that appears, is that there's actually a dichotomy in the dynamics of SGD. Unlike these deterministic methods, which I was talking about before, like gradient descent and everything, those things just converge and they're always the same rate. With SGD, you can actually show that there is a certain step size, which if you are below this step size, you get a different rate of convergence than if you're above this step size. It's very weird. And you can prove all of this just from renewal theory results for general measures. I did it here for the Marchenko-Pasteur. And what you see in terms of the rate itself is that the rate kind of freezes. So when you're below this critical step size, you get this like freezing behavior at the minimal eigenvalue. So the rate for it just depends on the minimal eigenvalue. When you're above this critical step size, the rate is completely different. It's just some horrible expression. But they have different rates overall. So it's really, really weird. And they agree when gamma is equal to gamma star. So these two rates actually equal each other when gamma is equal to gamma star. Okay, but it's really cool that you see this dichotomy. You see this sort of freezing effect on one side of the step size and this sort of like crazy thing on the other side. And just to show you this, you can actually plot the step size versus the rate. So at the bottom here are the step sizes, and the y-axis are the rates of convergence. So on one side, you can see you're just basically very stable, very linear. It's the exact same thing. Then all of a sudden, you get above this critical step size choice, and you just go haywire. It's also interesting that it appears that the optimal step size is not the critical step size, but is like slightly over it. So that if you wanted to get a faster rate of convergence, you should go a a little bit larger, but you risk the chance of being more unstable. But it's really weird. No, I've never seen these critical step sizes talked about in SGD. I'd be really interested if people were interested in doing something like this or understanding this more. Like I said, our biggest roadblock right now is actually the Voltaire equation, solving it for large scale matrices. It's a little bit troublesome. But again, this is all kind of work in progress, and I think it's really cool, and I wanted to share it with you because it has everything, FDEs, renewal equations, everything's in it. So I just wanted to kind of end with some sort of open questions. So I showed you guys the sort of general framework for basically doing average case analysis. Like I said, we've been really looking into SGD. I think there's a lot of questions with SGD now that we sort of have this sort of result, but we've also been looking at trying to do this for other measures, like really giving average case analysis for sort of the random features model. And then there are questions, I think even people were asking about it. Well, what about different matrix ensembles, spike matrix ensembles, for instance? Can you do this for non-convex functions like matrix completion, PCA? And I think the big one that would be of great interest to a lot of people is a signal, especially signal processing, is can you do this for sort of the L1? So if you have a 2 norm of AX minus B norm squared, and you add an L1 kind of penalty, can you get something which is just spectral for these algorithms and understand exactly their convergence properties? So I think there's lots of areas to work in, and I'll end here. And so thank you. If you have any questions, I love to hear them. So thank you very much.
Hey, thank you very much, Courtney. I think we have plenty of time for questions, so please go ahead, type things in the chat, or just unmute yourselves. If we do that in a disciplined fashion, then that should also work.
Can I? Okay, sorry.
Yeah.
Please go ahead.
Courtney, are you familiar with the EM algorithm? I'm sure you're familiar.
Yeah.
So if I have, like in statistics, there are many, I'm from a stat group, by the way, at McGill. So if there are, I mean, there are statistics models where we are trying to do like maximum likelihood estimation. And the actual likelihood is not convex. I know you mentioned that at the end of the open problem list. But let's say I run an EM algorithm where at each iteration, I am working with a convex function. Like in the M step, I have the actual objective function is not convex, but when I play with the EM in the M step, at each iteration, I am doing a convex optimization. So, but the actual objective function still is non-convex. So, what is your opinion on that? Like using this result in that context?
So I think. To be honest, I think there's we're at the tip of the we're at the tip of the iceberg. We haven't explored other algorithms. We really just focused on least squares because it was the easiest one for us to analyze at least. But like I think that this type of sort of analysis can be expanded to other things. We just haven't had the chance of doing it. Every time I give this talk, there's always like a new question that someone asks me, like, can you do it for this one? I'm like, I don't know. I'm like, I barely got my things done. But no, I think it is possible. I think there's a ways of doing it. I think also there's still questions in even the least squares from the statistics because it's related to sampling. Like all of this is in some sense some sort of sampling process. That kind of question could easily, we haven't really looked at either, like sort of more finite n dimension stuff would also be very interesting.
Thanks.
Yeah.
Thank you.
Yeah.
I want to ask kind of very naive questions. So the average case, to understand that the average case is like you can think of it as L1 norm or something, and the worst case is like a soup norm.
Exactly. Yeah, that's right.
And so for the complexity, can you say, okay, so let's compute like not the L1 norm, not the soup norm, not the infinity, but I don't know, L2 or some
in between type.
I'm not sure if there's any good answer to that, because
well,
if the answer is something horrible, then it probably is not so interesting. But
no, I think maybe the one which is kind of like quasi between these two is how they analyze the simplex method. So so we should be a little careful. Like average case is kind of like there's not a definition. Like it's kind of up to the person to create what do you mean by average case. I think the most naive average case is kind of what I said, which is like you average over all the inputs. But what people call also average case is what they did in the simplex method. So in the simplex method, you look at sort of the worst case and you perturb the worst case by a small amount. So you take the worst case and you add a little perturbation to it. And then you compute the complexity over that perturbed sort of worst function. That's kind of what John was also suggesting of doing. It's doing like a perturbation of your inputs a little bit and seeing what happens. And if you do that, it does produce faster results. Like it gives the right answer in some sense for a simplex method.
And something completely crazy like Newton's method, like the runtime of that. I know that in dynamical systems, by running Newton's method on some sort of strange initial conditions, you get some very interesting and complicated behavior. But
no. So the issue, I think the biggest issue with doing second order, I would love to do second order. So Newton's method is sort of a second order because it requires a Hessian. Is that you can't do it on the quadratic problem because the Hessian is, there's like, it's finite. I mean, it's just fixed. You would converge basically in one step kind of a thing. So you can't do it on that. So it's more related to being able to analyze other types of objective functions. And then I think you could easily do something like a Newton's method, but you have to just move, you can't do it on the quadratic. So it's going to require a little bit harder objective function. But yeah, no, I'm totally, I would love to do it. So yeah.
For solving large sparse in the square problem, we often use LSQR or CGLS. I don't know if you have any comment on this algorithm.
It's a good question. So we started with a master's student, or sorry, not a master's, an undergraduate project, honors project in math to do sort of try and model sort of sparse matrix, like sparse problems, like the matrices are sparse. They just give different eigenvalue distributions. So there's that problem. But what's really an issue is that random matrix theory hasn't really caught up yet. So like, I'm not a random matrix theory person. And the theory of sort of the behavior of the spectrum for these models aren't as well known, basically. We don't have good answers. They don't have good answers yet, and I've just been using their results. So if you want to do things where you're assuming sort of B is sparse or A is sparse, I need more of a random matrix theory person, basically, to help me, because I just use the theory. I don't actually, I've never actually created a new random matrix theory result. But yeah, I think it's plausible. Like all of this is, you can analyze these algorithms. Like you could analyze it.
How about the constraints?
Sorry, what?
So if you have constraints, like a non-negative constraints or the linear constraint?
Yeah. So this is a good question. I started looking into this. Yeah, I think you should be able to try and do some of these with the constraints. My experience is even in LPs that the constraints, you get different convergence behaviors. Like there's different regions where you're in where you have sort of like different looking convergence behaviors. Like there's a region where like you're not satisfying the constraints per se, like you're kind of wandering around, you're not exactly satisfying it. It looks different once you get into sort of where you're on your active set and really you're not changing very many of the constraints. That's a different convergence behavior. And I don't know how the random matrix theory will work with that, but I do think it's a valid question, and I would love to explore it. Like if people are interested, I think there's tons of questions, and I would love to do these. I think this model it works for a lot of different things. Yeah, thanks. Are there other questions?
Maybe I can ask.
Hey, Tom.
Hey, how's it going? It was a great talk. So I'm really interested in this Voltaire equation. That's really, can you give me a hint of where it comes from? Like what's behind it?
Oh my gosh, it's a mess, y'all. It's a mess. Well, I mean, I know that you had done some work with the empirical, like showing concentration with the empirical one. It's new concentration of measure results. It's everything. It's like 60 pages long. It's a horrible thing. It's pretty messy. Like the air terms in it are there's martingale air terms. We did it with martingales. It's horrible.
Okay,
but
well,
yeah, I would, if you're interested. I mean, Elliot's here. Right. Elliot, you want to say hi to Tom? Oh, you did? Okay.
Yeah, I already emailed him. But yeah, I mean, I'll look into the paper. I'm interested to see what's behind it.
Yeah, we thought it was going to be really easy, and it turned into a huge. Yeah, it was not easy. It's the first conference paper, as Elliot has put out, has been keen to saying, where the appendix is 70 pages long and the conference paper is like 12 pages. So, you know.
That's great. Okay.
But yeah, if you're interested in other algorithms, like stochastic ones, other stochastic things, I think there's like a lot of other stochastic algorithms which are less known about their dynamics. So like SGD is more well known what happens, but there's other ones which are not as well known, and I think we can analyze them. So,
yeah, I'll read your work and try to catch up, and then I'll message you and we can talk more.
Yeah, that's great. Thanks. Yeah.
Great talk.
Sorry, are there
more? Are there more questions?
Oh, someone asked, is there what's the gap in extending the analysis? It's a good question. Part of it, what makes linear regression so nice is that you can just write down a formula easily for the gradient and see how it depends on the spectrum. For more complicated general models, like even logistic, it becomes less clear how, the gradients are more complicated, and it's not as obvious that it's just spectrum. There might be more involved, like the eigenvectors might actually start to play more of a role in those.
Okay, maybe I have one last question to wrap up this session. So just philosophically, can you make any inferences from your halting time average case analysis that certain algorithms aren't as bad as people made them to be when they focused on the worst case analysis, which is kind of a Nesterov school type of thing?
Yeah, so it's interesting. So like in the deterministic setting, in the deterministic setting, they all kind of have the same flavor. Like they all kind of match what you would expect. But in the stochastic ones, that's where things might actually get really interesting, because there's much more of a gap between what people actually see and what the worst case rates are. I guess like the bigger that there's a gap, like you know, like that what you see in practice versus what you actually like the worst case rates are, the more this chance has of working. So I think stochastic probably has a better chance of that, and also like these L1 stuff. So I think like the worst case rates for those are not good at all, but I bet you the average case is a lot better, just because it shouldn't be like they're much better than they actually are. So I think that would be that's the area. Yeah, that's a good question. That's something I wanna do more of.
Sure.
So yeah. No, thank you, by the way. All these questions were great. I'm sorry if I couldn't answer all of them. I think there's lots to do. So,
I mean, I think we should wrap up. I think the turnout was probably at the peak a maximum for this year, which is easy, but also including last semester. So there was lots of interest, and I think the question period also reflected that. So let's all thank at least everybody who's still here. Let's thank Courtney again.
oh, thanks. And if you guys have more questions or interest, let me know. I'm happy to expand